Hello and welcome to NPTEL MOOC on Applied Electromagnetics for Engineers. In this module we will continue the study of uniform plane waves. We have already seen that waves can propagate along the z axis, can propagate in any arbitrary direction. We have seen that the waves that we are considering are transverse electromagnetic waves, but we have always assumed that we have either Ex component or Ey component and the corresponding Hy and the minus Hx component, but it does not have to be so. Because the wave equation that we derived is a very linear equation, you can have an electric field which has both x component as well as the y component. So, you will have a superposition principle applicable over here because the equation is linear, and which means that the electric field will have Ex as well as Ey component at the same time. Okay. But before we get to that, we will recall what is the assumed dependence of Ex on z. We can write the dependence of Ex on z by specifying the phasor notation. In the phasor notation we have Ex0 e power minus j beta z, and Ey of z will be some amplitude Ey0 e power minus j beta times z. Of course, it is also possible for the Ex and Ey components to exhibit as some kind of a phase difference. So, you can write this as e power minus j beta z plus phi. Okay. Please remember, Ex and Hy are one group and Ey and minus Hx are another group for the TEM waves that are propagating along z axis. So, along the z axis you can have an electric field which has both Ex and Ey components. So, if this is the wave direction, this is the z axis, the electric field can be in a direction that will have both x as well as y, and the corresponding magnetic field will also have a component of Ey and minus Hx. So, E cross H must be along the z axis. So, appropriately you will have to find another field such that this E cross H would be perpendicular to E. So, the point is, because of the linearity of the wave equation, simultaneously both Ex component can exist as well as the Ey component can exist. Okay. But as I said, there can be a phase difference between the two components. Depending on this phase difference, there will be different type of a behavior for the electric field of this wave. So, whenever we talk of a wave, we normally specify its electric field. Okay. Why do we do that? Because the magnetic field can be obtained easily from the electric field. We have already seen in the previous case how to obtain the magnetic field from the electric field. So, it is possible to always obtain the magnetic field either by applying Maxwell's equation or by the rule that we developed in the previous module. Therefore, we usually resort to only specifying the electric field. Okay. And of course, that electric field will be in the form of a wave which we have assumed to be a sinusoidal one, and we are writing the corresponding phasor notation for those. Okay. So, these components all have the same frequency omega. So, both Ex as well as Ey are at the same frequency omega, and they also have the same propagation constant beta, except that there might be some phase difference between the two. Okay. Suppose we consider the phase difference phi equal to 0, then what will happen? The total electric field E, which is a function of z and of course is a phasor, but I am not writing the phasor tilde everywhere, okay, because it becomes little cumbersome to keep carrying the tilde. I am dropping this, but please remember, all that we are talking about are phasors only, okay, at least up to the point where before we introduce the time dependence t. So, E of z phasor will be equal to x hat Ex of z, which is another phasor, plus y hat Ey of z, which is another phasor. Now, when I go to phasor to time domain, okay, I can do that. So, I will have the real electric field in terms of z and t given by x hat Ex0 cos omega t minus beta z plus y hat Ey0 cos omega t minus beta z. Why is that both components have cos omega t minus beta z factor? Because phase is assumed to be 0. Now, this is the electric field of the wave propagating along the z axis. So, propagation along z axis, you can write the corresponding magnetic field, but we are not interested in that at this point of time, because whatever we talk of electric field, the same thing for the magnetic field as well. The amplitudes Ex0 and Ey0 can be different. Okay, so it is not necessary that both components have the same amplitude. Now let us imagine that we pick a convenient plane. Okay, we pick a plane which will make this beta times z term to be a constant. So we pick that plane to be z equal to 0. So in the constant z equal to 0 plane, so in the constant z equal to 0 plane, okay, what will happen to the total electric field E? E at z equal to 0 as a function of time will be equal to x hat Ex0 cos omega t plus y hat Ey0 cos omega t. Okay. Let me draw two lines. I call this line as x and call this line as y. Why is it that I have written x down and y here? Because I am actually looking from the top. So this would be the z axis. Okay, so this is the z axis, and if you look from the top, right, you have an x axis and a y axis. Okay, and the wave is propagating along the z axis, which means if I look from the top, the wave is actually coming towards me, and I have cut a certain plane. I have cut this plane at z equal to 0. That is just my reference plane. I mean, there is no reason or rhyme why z equal to 0 has to be constant. You can make you can take another plane z equal to z1, where only condition is that beta times z1 should be a constant. Okay. So now that I have written my x and y axis on this plane, and I have shown you that I am actually looking towards the wave traveling towards me, let us see what happens to the direction of the electric field at t equal to 0 or at omega t equal to 0. At omega t equal to 0, what will be the direction of the electric field E? It will have x hat Ex0 plus y hat Ey0. So the resultant will be depending on the ratio of Ey0 to Ex0, but it would definitely be along that direction. So let us say this is the direction. Let me use a different color to show you that the projection of this electric field E at omega t equal to 0 on the x axis will give you Ex0, the projection of this one on the y axis will give you Ey0. Okay. The angle with which this vector lies initially at omega t equal to 0 with respect to the x axis is, we denote this by theta. Okay. And this angle is given by tan theta equal to Ey0 by Ex0. Okay. Of course, this tan theta will be equal to 1 and theta will be 45 when the amplitudes of both Ex and Ey components are same. If they are not equal, then they will not be same angle. Now tan theta is so and so, right. What happens at omega t equal to pi by 2? Cos pi by 2 is 0. So which means electric field at omega t equal to pi by 2 will be at the origin, because well, the amplitude is 0. What will happen at omega t equal to pi? Cos pi is minus 1 and you will get minus Ex0 minus Ey0 y hat, right. So this was the condition that we had at omega t is equal to pi by 2, but at omega t equal to pi, the direction of the wave will be along minus Ex and minus Ey, right, which would be along this particular direction. So this is when omega t is equal to pi. What will happen at 3 pi by 2? Cos 3 pi by 2 is 0. So which means it would again be back at the origin. So if you look at what is happening, you can see that the wave is executing a motion such that it initially starts off with this point, goes through the origin, goes through pi point and then comes back. So it initially goes in this way, right, and then comes back. So essentially it is going along this particular line. Happily it is going along this particular line from one point to the other point. So it is oscillating along a line. Okay. So that type of behavior is what we call as polarization of the wave. We said that the wave is polarized along a line, and a line polarization is also called as a linear polarization. We also specify the angle of this line that makes with respect to the x axis. So this is a theta linearly polarized wave, okay, where the angle theta is given by Ey0, tan theta is equal to Ey0 by Ex0. Well, it does not have to be that the waves are polarized along a line. Waves can be polarized in a more exotic state. One of that is called as a circular polarization. In the circular polarization case, we require that electric field and magnetic field have some amount of phase difference. Okay. So when I consider phi to be non-zero, I have to modify these equations, right. So the y component cannot be minus beta z, but there has to be a phase phi component. So let me just write this as plus phi. Okay, doesn't matter, I could have written it as minus phi, but let me just write it as plus phi. Now if I assume that phi is non-zero but phi is equal to pi by 2, what will happen? I have some cos of x plus pi by 2. What is this? This is equal to cos x cos pi by 2 minus sin x sin pi by 2. So clearly this fellow is gone, so you will get minus sin x. So this is what I have, right. So my electric field E at z equal to 0 plane will be equal to x hat E x 0 cos omega t minus y hat E y 0 sin omega t, correct. I will also assume that the amplitudes of these two are constants, therefore this would be just E0 and this would be just E0 again. So the amplitudes of x and y components are same. As before, let me draw the lines over here, call this as the x axis, this I call as the y axis. Of course, as you know, I am looking at the wave as it is approaching me. Okay. What will be the initial direction of the electric field at omega t is equal to 0? At omega t equal to 0, the direction will be at along x axis. At omega t is equal to pi by 2, because cosine pi by 2 is 0, the direction will be along minus y hat. Then when omega t is equal to pi, the direction will be along minus x direction, and at omega t equal to 3 pi by 2, the direction should be along plus y direction, because sine of 3 pi by 2 is minus, therefore this would be along plus y direction. So let us plot these directions. At omega t equal to 0, I am along the x direction with an amplitude of E0, right. This is at omega t equal to 0. Then what will happen? At omega t is equal to pi by 2, the direction is along minus y, but minus y means along this direction, right. So the direction for the wave, or the wave will be at this point. This would be at omega t is equal to pi by 2. At omega t equal to pi, you will have the wave propagating, or the wave electric field directed along minus x, which will happen along this way. So this is where I have the wave at, so this is the wave here, this is the wave later on, this is the wave at omega t is equal to pi. Finally at omega t equal to 3 pi by 2, we have the wave along the y axis. So if you look at this, it is as though the waves, it is, of course, the wave starts at E0, along the x axis, and it continues and makes a circular motion in this way. It is making a clockwise motion in this particular way. Okay. If I now imagine that if I curl my fingers along this, so this is the plane, and if I curl my fingers in this direction, I see that this thumb will be pointing in the same direction as the wave propagation. And remember, I am actually looking from the wave from the top, and it seems as though that the electric field line is executing a motion such that if I curl my left hand left hand, then I see that as the wave is approaching towards me, the electric field is making this left-handed motion. Okay. So such a wave is called, or is said to have, a left circular polarization. Okay. So this left circular polarization is when you look from the top to the wave and it makes a left-handed motion. Okay. You can take this as an exercise. Okay. What would happen when phi is equal to minus pi by 2, and then show that the corresponding direction in which the wave electric field vector, the tip of the electric field vector would rotate, is in the other direction, is in the direction of the right hand kind of a motion. So you have a left circular polarization, a right circular polarization, you have a linear polarization. All these polarizations are how the electric field, the tip of the electric field vector would behave with respect to time in a constant plane. Okay. One of the frequently asked question is that if I have a wave which exhibits this circular motion, is it possible for us to implement some kind of an optical or some kind of a converter such that I convert a circular polarized motion into a linear polarized motion, or sometimes I have a linear, I want to convert it to circular. All these things are possible. They all require that we understand how the wave propagates in a anisotropic medium, which is the subject of a future module. But yes, polarization converters are one of the most common elements that you would find in the EM wave community, in the optics especially, in the optics community especially, you would find lot of experiments involve the use of polarization converters. Okay. Further, these polarization vectors can be thought of as the unit vectors themselves. So, you have a polarization vector. If you have a circular polarization, you can define a unit vector along the circular and a unit vector along the radial, right circular, and combine them, and the resultant will actually be a circular polarized light. Okay. So, you have a circular polarized wave expressed as a linear combination of left and right circular polarization, just as we have in fact in the previous case we have shown you that left circular polarization is expressed as sum of two linearly polarized waves. One linear polarization was along x, the other one was along y. Okay. So, these two are what we call as a basis, mutually orthogonal basis. Okay. So, one allows you to express the other component in terms of that particular unit vectors. So, this completes our elementary discussion on polarization. We will revisit polarization in the context of polarization conversion when we talk of propagation through anisotropic media. Okay. We now move on to other topics. Well, so far we have considered a uniform, lossless, right, homogeneous, isotropic medium. The meaning of each of this is that uniform and homogeneous means that the components mu and epsilon are independent, they will have the same value at different points in space. Isotropic means that if the wave is propagating along x direction, the value of mu and epsilon is the same. If it is propagating along the y direction also, it is the same. If the wave is propagating along z direction, mu and epsilon are the same. Lossless media means that we do not have, the wave amplitude does not attenuate as it propagates along the wave. So, if you look at the wave amplitude at z equal to 0 and you look at the wave amplitude at z equal to say 5000 kilometer away, the amplitude would remain the same. Okay. Instantaneously there will be change in the amplitude, but if you wait for the time period, then eventually it will go back to the same amplitude as does the other point. So, there is no reduction in the amplitude, there is no reduction in the power that is carried by the wave. We will talk of power being carried by the wave slightly later on. Okay. So, we now want to consider what happens when the wave propagates in a lossy medium. Of course, I know what happens when the wave propagates in a lossy medium. Remember this component gamma that we derived in the case of a transmission line? Well, gamma was given as alpha plus j beta, and we had defined this one as square root of r plus j omega L into g plus j omega C when the transmission line had resistive and conductive components, right. So, we rewrote this one as the real part and the imaginary part, and then we said that alpha is the attenuation coefficient. Pretty much the same thing happens, except that we have kind of identified L with mu and C with epsilon of the medium. What should we identify this R and G with? It turns out that we have to identify it with the constant sigma, which is the conductivity of the medium. Okay. If the conductivity of the medium is equal to 0, then the medium is a perfect dielectric medium. Okay. If the conductivity of the medium is equal to infinity, then this is a extremely good conductor or extremely perfect conductor or perfect conductor in some sense. So, if I consider a medium, so this is the medium that I am considering, and the wave is propagating along the z axis with its electric field oriented along say x axis or y axis, whatever that is, and there will be a corresponding H field over there. If the medium, in addition to be described by mu epsilon, also has some amount of sigma, what will happen to the wave as it propagates? Well, we go back to Maxwell equation to see if the wave equation that we derived will remain the same, and it turns out that it will not be the same. So, you have del cross E equal to minus j omega mu h, no problem, but del cross h we had so far assumed to be equal to j omega epsilon times E and neglected the current density component, but you cannot neglect that current density component anymore. Because of finite value of sigma, the current density component, which is proportional to E and therefore given by sigma E, the point form of Ohm's law as we discussed, this is equal to sigma times E plus j omega epsilon E. So, this term cannot be neglected and must be included. Okay. As before, we take the curl of the electric field once again and substitute the right hand side of curl of H. Okay. So, I obtain minus j omega mu times sigma plus j omega epsilon times electric field E. Because the left hand side can be simplified to del square E, and the right hand side has become minus j omega mu sigma plus j omega epsilon times E. Okay, minus sign and minus sign can cancel with each other. This complex number, which is j omega mu times sigma plus j omega epsilon, we call this as gamma square. We can reduce this del square E into some del square Ex by del z square, assuming that the wave is propagating along the z axis and z axis alone and has a component of the electric field as only the Ex component, and the right hand side will be gamma square times Ex, where this gamma is given by square root of j omega mu into sigma plus j omega epsilon. Okay. And of course, gamma will be equal to alpha plus j beta. You can derive the expressions for alpha, you can derive the expressions for beta. I will not really do that one here, but one case is actually very interesting. This case leads to what is called as the skin effect in the conductor, and it is applicable when gamma can be simplified, okay, by taking an approximation which I will just show you. Remember, recall gamma is j omega mu sigma plus j omega epsilon, right, all under square root. If I assume that sigma is much larger than omega epsilon, okay, if I assume that sigma is much larger than omega epsilon, which is equivalent of assuming that sigma times E is much larger than omega epsilon times E, okay, in magnitude of course I am talking about. So, magnitude of sigma E is larger than magnitude of omega epsilon E, and omega is time variation, right, time variation converted in the phasor form in terms of the frequency variation. So, this component is essentially the displacement current and this component is the conduction current. So, if the conduction current dominates the displacement current, as in would happen when the medium is made out of a copper, for example, right. So, you have a nice thick copper plate over which we are trying to, or within through the medium that is trying to propagate. In that case, because of the conductivity of the copper being very high, and for the typical operations of the frequency, the value of sigma will be much larger than omega epsilon. This indicates that the conduction current or the current density in that medium will be mainly conduction current and extremely negligible displacement current. So, for that case we call this as a good conductor. So, we call the material or the medium as a good conductor when sigma is much larger than omega epsilon. What will happen to gamma then? Gamma will be approximately j omega mu sigma under square root. Okay. Now, this can be written as square root of omega mu sigma times square root of j. What is square root of j? One simple trick to find this one is to write this as e power j pi by 2 and then take a square root. Luckily, taking a square root means you multiply this one by half. So, this becomes e power j pi by 4, and e power j pi by 4 is nothing but 1 plus j by square root 2. So, gamma will then be equal to omega mu sigma by 2 under root, right, times 1 plus j, indicating that this has alpha equal to omega mu sigma by 2 under root and beta also equal to square root of omega mu sigma by 2. Okay. So, both alpha and beta are equal and they are equal to root of omega mu by 2. Okay. What will happen to the electric field then? Well, we know that Ex of z we were considering, the phasor of the electric field that we were considering. Let us say it has some constant E0 and it must be e power minus gamma into z. This is the general solution that we are considering, okay, and we will consider that z greater than 0 is where the medium is present. Therefore, we have put in a minus sign to this one, so that we eventually want the wave to attenuate, not to amplify. Substituting for gamma as alpha plus j beta and knowing that this alpha is given by omega mu sigma by 2 under root times 1 plus j here for gamma, I can write this as E0 e power minus alpha z e power minus j beta z, but E0 or this particular thing. So, alpha is given by square root of omega mu sigma by 2 and 1 by alpha if we define as delta, and delta is given by 2 by omega mu sigma under root, and delta can be simplified further by writing omega as pi 2 pi into f. This is given by 1 by pi f mu sigma under root. Okay. So, if I define 1 by alpha as delta, then I can rewrite this one as this expression for electric field as E0 e power minus z by delta e power minus jz by delta. Okay. And delta is what we call as the skin depth. Okay. It is measured in meters, you can go back and show that this is actually measured in meters. And for 4 delta, so if z is such that the distance, if you travel a distance of 4 delta, then the amplitude would be e to the power minus 4 times e to the power minus 4, and e power minus 4 is such a small number that this is approximately 0. So, we say that as the wave begins, so at some z equal to 0, let us say the wave enters into the medium, a good conductor, and as it begins to propagate in terms of z for about 4 delta, the value of the electric field would have dropped down almost to 0. Okay. So, this delta, which is the skin depth, constitutes, or is a very important parameter to describe whether the medium is a good conductor, and if it is a good conductor, how within to what distance inside the good conductor the wave can actually propagate. Because if delta is very large, right, when delta is large, then you need to propagate further such that the wave actually drops down in amplitude. But if delta is very small, then which means that for very short distance right after the conductor, the wave actually drops down. Most importantly, the skin depth is not independent of frequency. That is a very important factor to remember. Skin depth is inversely proportional to f. So, the same medium which might be having a very large value of delta for a small value of frequency, the corresponding value of delta will actually start to decrease as the frequency increases. Okay. So, if you had initially considered a conductor or a wire, a solid conductor, let us say, the current through this conductor would be uniform at f equal to 0, because at f equal to 0 the current or the current density, which is proportional to the electric field, will be having a skin depth of infinity, right. So, which means that there is absolutely no attenuation as the wave goes through this conductor. But at very high frequencies, what you will see is that the current is kind of confined only along the edges within this particular material. Okay. So, at higher frequencies the current is just confined to this thin strip, okay, and the width of this strip is given by the skin depth delta, and this width keeps decreasing and decreasing. When the frequency goes off to optical frequencies, then the skin depth will be equal to very small number, provided you keep the same value of mu and sigma. We will have more to say about skin depth. We will in fact have a quasi-static analysis of skin depth in the next module. Until then, thank you very much.